Swayam Prabha. Digital India. Educated India.
So hi students, hope you all are doing well. Welcome to another very exciting session of the course Soft Tissue Characterization and Applications. So far what we have learned is the different kinds of soft tissues. We have learned a little bit about their structure, kind of revisited their anatomy, which we may have taken in a class of biology earlier, and we have kind of looked over all the different organ systems as well as like the different soft tissue components from the human head to the toe. So in today's session we are going to talk further and get a little bit into the mechanical properties of such tissues. So let's get started. Okay, so mechanical properties, when it pertains to soft tissues, we sometimes also call it as biomechanical properties, because these are biological tissue specimens, right? So that's a term which is used fairly interchangeably with mechanical properties. And then biomechanical properties can be obtained in different directions. One example is the uniaxial, which is the most common way of deriving the mechanical properties. Then you have biaxial, it can also have multi-axial. Axial basically means it's a certain direction in which you're applying the force to a certain specimen, right? Typically there are instruments which have been there for a while, and they have got more and more advanced with time, like in terms of the amount of sensitivity they can have, or the amount of automation they can have. They are usually known as universal testing machine, or the UTM. Okay, so what you're seeing here on the figure on the top right is basically a soft tissue specimen which is clamped in between the grips of a universal testing machine. Okay, so typically you clamp it from the bottom and the top. The top usually is the one which moves, so there is a displacement which happens on the top, which is induced displacement, and due to that displacement there is a force value which is measured using a load cell, right? So then the force versus displacement data is usually plotted, and from that you finally get the stress versus strain. So this is the overall scheme of things, how we look at mechanical properties. And this is not only specific to the soft tissues, this is for any material in general. Whenever you talk about mechanical properties of any material, you are looking at majorly testing these tissues within a UTM and measuring the stress versus strain, which is going to be derived from the displacement versus the forces, right? Displacement, like I've said, can be measured in terms of how much the tissue has moved. Typically this is back calculated from some certain gears, how much they have moved, and from the, we call this as a crosshead, and it is going to move along a linear direction, along a line, right? So this is the uniaxial, so it only the test is only performed along an axis, that's why it's known as uniaxial, right? And the load cell, which is typically present as a part of the bottom of the instrument, which will take the forces which are generated. So force versus displacement converted to stress versus strain, right? There are several considerations which have to be taken while testing soft tissues. So soft tissues, as we all know by now, is very soft, and they can range from the hardest one is the skin. We are going to take some examples how the different soft tissues compare in today's session, and one of the most softest one is the human brain, for example. So some of these tissues may clamp well and may test fine, where the other ones are not going to test that easily. They're going to break as soon as you apply a little bit of displacement, right, or a little bit of load. So that is where the concern is. You have to have grips to hold or clamp it on both the sides, on the top and bottom, which are much more suitable for soft materials such as the soft tissue. So the grips need to have some kind of extra friction and some sacrificial material like a like a paper gauze or something like that in between, which can hold the tissue in place, and the tissue is not held by the metal in general, because metal can cut through it, it can shear through it, and if you tighten the clamps way too much, it is going to break from the ends, right? That is also an important consideration. But if you tighten it too less, then it can slip from the clamp. So there are a lot of considerations which goes into testing of soft materials, especially the soft tissues, which also has a component of hydration. So they are slippery, they are hydrated, right? So having said that, let us look a little bit more into how a uniaxial test is being conducted with soft tissues. So typically a test specimen, you can have the test specimen in the form of a rectangular specimen which has a certain depth or thickness, that is typically the norm, or you could have a specimen which you can cut in the shape of a dog bone. These are typically not possible that much for soft tissues which are extremely soft. For metal specimens, if you look at any of the characterization or mechanical characterization studies, they're usually in the shape of a dog bone, and that's there for a reason, right? This is for the nice and uniform stress distribution. That's the reason, right? So the tissue specimen which you get in the form of a rectangular specimen is typically clamped in a way that its length is parallel or longitudinal, these are interchangeable terms, to the direction of the load application. So if we are pulling a specimen like this, the specimen should be clamped in a way that it is, the rectangle is not like this, it is like this, because it is being pulled. So it's along the length, right? That is what is known as longitude. I had just explained about the specimen in one of the sessions previously, where you can cut the specimen in any directions or orientations or for different parts of the body, like if you're talking about skin, but all of them will have a very different property per se, right? But if you're taking a brain specimen, you have to know whether you're taking it in the direction of the fibers or vertical to the direction of the fibers and things like that, so that's the concept of anisotropy due to the fiber direction and how we are cutting the specimen. So that is very uniquely important here, that how do you choose your specimen, and then you define your specimen and then clamp it in a way that this is longitudinal and facing along the direction of the load application. So that is step number 1. The next step is the bottom clamp is fixed. So the bottom clamp is usually fixed, it doesn't move, and it is a constraint which is applied, right? The top clamp is displaced at a certain rate, which is also known as the displacement rate. This is typically given in the terms of millimeters per second or sometimes millimeters per minute. You will never see terms like meters per second, because that's way too much, right? Like you're looking at specimens of the size maximum 5, 8 or 10 centimeters in length. You cannot be applying a meters per second there, that is way too fast, right? You will not be able to control the test. So these are usually the displacement rates at which you will be pulling the specimen. This is displacement rate is sometimes alternatively known as the strain rate, but strain rate actually is not something which depicts the displacement directly like on a mathematical notion, even though they do have a correlation. So strain is a little different quantity which I'm going to define as we go down the bullets here, and let us just revise what stress and strain is before we define what strain rate is, right? So typically, let's assume this is displacement rate. There is a certain rate, some millimeters per minute or millimeters per second. I'm pulling the specimen using the device. So after a certain point and beyond a certain strain or beyond a certain amount of displacement, the tissue will tend to rupture, right? It cannot just keep on pulling forever. Like after a certain point, the tissue will break, right? And once the load drops significantly, that is how you can detect that rupture. All of a sudden you keep on pulling the specimen and the displacements are going on, the load cell is getting loaded like with more and more forces. All of a sudden there is a sudden drop in the force, that means there is a break or a rupture of the soft tissue, right? That is how you detect a rupture. Once the load drops significantly, the test stops. That is kind of set within these machines, that once you see a sudden drop in the load, just stop the test, right? So that it doesn't keep on going and there is some accident or clamp keeps on rolling. So it's an auto stop. During the experiment, the fibers within the tissue stiffens and it aligns more towards a load direction. Now, what does this term actually mean? So, when you first get a test specimen, typically you will not be an expert in the anatomy of the human body, right? Like, you may or may not know how the fibers are aligned. If you know, that is great. You know clearly that this is towards the length of the fiber or this is vertical to the fiber. Let's say you know or doesn't, you do not know, but typically what you do is, like, there are certain fibers which are completely along the direction of the load and there are certain fibers which may be away from the direction of the load, right? So when the experiment actually starts, all the fibers are not properly oriented towards the direction of the loading or towards the direction of the pulling. They may have a 5 degrees or a 17 degrees or 25 degrees, whatever it is, like, but it will never be properly aligned, right? That's the characteristics of the specimen, unless you're doing a really good job in figuring out the anatomy and cutting it from the sides, right? So let's assume there is a certain fiber angle to the direction of loading. So as you keep on loading the specimen or displacing the specimen more and more, the fibers are going to align more towards the loading axis, and that's why typically you do not have a linear response, force versus displacement response, for these kind of soft tissues. So what you see here on the graph on the very bottom right, you're looking at a soft tissue response, which is the bottom hard black line plot, where what you're looking at is the stress versus strain, which is kind of an adaptation of the displacement versus force versus displacement, where force is in the y-axis, displacement x-axis. Similar, if you divide force upon the initial area, which I'm just going to explain, you will get stress, then displacement divided by the initial length will give you strain. So these are normalized quantities. Stress strain plot of a soft tissue would typically look like this, kind of hyperbolic up, so something which kind of bulges up. It is not a single linear line. So if you were to look at any of the engineering materials, typically you will have a very linear profile between the stress and the strain. That's why you can very easily define what is known as a modulus of elasticity. Modulus of elasticity is one of the most common terms you will encounter while talking about mechanical properties, besides another term which is known as the Poisson's ratio, which I'm going to explain in the upcoming like slides and so forth. So from a elastic modulus standpoint, elastic modulus is nothing, or modulus of elasticity, or sometimes you known as just modulus by itself, given by the symbol E. That basically shows the slope of your plot, slope of your stress upon stress strain plot, right? Stress along the y-axis, strain along the x-axis, right? So the slope of this plot, typically for engineering materials such as metals and other hard materials, are fairly linear. But for soft tissues, it is not linear. It has a very small linear segment in the beginning, but after that it keeps on going in a very non-linear pattern and kind of keeps on going up. This is exactly what you see here for the soft tissue. So in the soft tissue, you can see here in the plot on the bottom right, three phases. I was talking about the first phase, where the fibers are kind of intertwined and going in different directions and not really focused or aligned towards the loading axis, right? As you go with more stress basically means you're loading the specimen more and more, then the fibers get more aligned towards the loading axis. That's the phase 2, right? So in phase 1, when the fibers were not that much involved, you get a fairly linear response, and phase 2 has a curved up response, followed by phase 3, when the fibers are totally aligned with the direction of loading. You have a much more higher response, and then finally you lead to the point where the fiber breaks. So typically if a soft tissue is undergoing a damage, it is not because of the matrix damage, it is because of the fiber damage. So there are two components in any soft tissue, like I had mentioned in the first class itself, that we are considering a range of fibers, either a unidirectional set of fibers or a multi-directional set of fibers going in different layers, which are part of the entire soft tissue system and embedded within a matrix, softer matrix. Fibers are usually the harder part. So typically like the initial phase where you're looking at, the fibers are not very well aligned, like I've said, towards the loading axis, so they are kind of misaligned. So majority of the loading is being borne by the matrix. So that's where you see the linear response. But once the fibers are totally loaded, as in as you can see in phase 3, there is a final point when the fibers will tend to stretch beyond its limit and it's going to break, and then that causes the final tissue rupture, right? And that tissue rupture will cause the entire load to drop and the test will stop, right? So coming back here, uh, the pull force, let us just go through the different quantities. We are talking about 4 quantities here as we speak. The first one is the force, second is displacement, third is stress, fourth is strain. So let's quickly go over what these quantities are, and let us be, all of us be on the same page, right? Like, because we are going to be using these terms again and again throughout this course, right? So the first one is known as a pull force. Pull force is the amount of force which is needed to pull the specimen by a certain displacement or a certain amount, right? So the pull force is typically measured by the load cell. Then that pull force will cause a displacement. So the displacement happens in the motor screws of the device, and that finally causes the displacement into the tissue specimen. So we are applying a force that is causing a displacement, right? This is very clear. The second part is stress and strain. These are derived quantities. These are not the actual or the measured quantities, right? So stress is given by the force at any point, because this force is keeping on changing, right? Initially the force may be very low and we keep on applying more force as we have to pull the specimen more and more, right? So the force at any point divided by the initial area of what? Area of cross section of the specimen, initial area of cross section. So let's say I have a rectangular specimen of the length 5 centimeters, then I have width of 1 centimeter and a thickness of 3 millimeters, right? So what is the area of cross section? It is 1 centimeters times 3 millimeters, right? That's the area of cross section. That's my initial area. So if I divide the force at any point by this initial area, so I'm just normalizing all the force points by the area, I'll get this stress value. So stress keeps on changing as we keep on pulling the specimen, right? Similar with strain. So strain is derived from the change in length divided by the initial length. Change in length is the displacement which is occurring, like starting with 0. So the specimen is at rest and we keep on applying 1 millimeter, 2 millimeter, 3 millimeter and so forth. So there is a change in length divided by the initial length of the specimen, that is 5 centimeters. We should make sure we have the right dimensional analysis and the right units. So if we are dividing millimeters by centimeters, we should convert the centimeters to millimeters to have the right normalization, right? So that is understood already. So that will give us the strain. So what do we see? As we keep on pulling the specimen at time t equal to 0 to, let's say, 50 seconds, we keep on pulling the specimens. What is going to happen is you are going to increase the amount of force which you are applying on the specimen. That is going to cause an increase in displacement, and these increases divided at different points by the area and the length respectively will give you the stress and strain. Stress is usually given by the units of Pascal, right? Force in newtons, initial area in meter square. So newtons per meter square is given by Pascal. Meter is a very huge amount of area. You usually what you would see is some millimeter square, right? Millimeter square. So newtons divided by a millimeter square will give you 10 raised to power negative 6 in the denominator, which if it goes up will lead to something which is known as megapascals. Okay, so majority of the tests we will measure the stresses in terms of megapascals, because we are using this terminology, we are using millimeters for all describing all the lengths and the measurements, geometrical measurements, and we are using newtons for describing all the loads. Here we just have a set of loads which is keeps on increasing, right? So this will give you stress typically in megapascals, and strain here is change in length, which is unit as millimeter, by initial length, which is again units in millimeters. So millimeters by millimeters is unitless. So strain is a unitless quantity. That's why whenever we talk about strain rate, it is the rate at which the strain is unitless strain is changing. So it has strain rate has the units of uh, divided by, or seconds negative, like per second, that's the unit for strain rate, but for strain it is unitless, right? So hopefully these terms are clear, what force is, what uh, displacement is, what stress is, what strain is, and finally you describe it using a plot. You have to just run an Excel or a MATLAB program to just quickly divide all these terms. The displacement and the forces in newtons is what you will get as the output from the machine, the UTM machine, right? And you are going to do the post processing. Some of the machines have this auto calculation, it will ask you to enter the area or ask you to enter the initial length, and it will auto divide it and give you the stress strain only. But majority of the devices what I've seen so far reports usually the displacements and the forces at different time points. So let's say there is a certain sampling rate of the machine, so every let's say 50 milliseconds or every 100 milliseconds it's going to take measurements, right? So take measurement of what? Force also, the displacement also. So you get a range of data of 2000 3000 points for maybe a 50 seconds test. All these points are different forces and the corresponding displacements. So I take this entire data and divide the all the forces by the initial area and all the displacements by the initial length, right? And of course there are certain other aspects, like the forces may not start from zero, it's a negative force and things like that, those we have to correct. But typically this is the norm, like you convert this into a stress strain data and finally you plot that in an Excel. Now there are few things which happen sometimes. The initially when you have clamped a specimen, the specimen could be a little slack. Slack means you have not completely like applied the initial needed load to the specimen, so it has a little bit of curvature, it's kind of just sitting like this, like with a slack, right? So this slack may lead to a negative force value, which you need to just subtract it and just make sure you normalize to start your plot from 0 0 only. 0 0 should be a starting axis, right? So this kind of subtractions or normalization can be done, right? So going further, the experimental data which I have just mentioned, generated by the UTM or the universal testing machine at multiple locations during the test and during multiple times, right? So there's a huge populated data set which comes out of this. Finally, once you have converted this data to stress versus strain and have plotted it, then you can find out the modulus of elasticity, which is given by the slope of this plot. Slope is nothing but tangent of theta. If you drop if you take any 2 points in this plot, so whenever I say plot, I mean this, like this hard black line which you're looking at going from 0 all the way up. So you take any two random points, right? Like in the close vicinity, not like in the ends, right? Like in the close vicinity, within a visual range, you take any 2 points and you drop a perpendicular, you drop a base, you take the tangent of theta which is perpendicular by the base, that will give you the slope of the curve at that location, and that is given by the modulus of elasticity. Slope is the same as the modulus of elasticity. What is its unit? It is unit is stress upon strain, so megapascal divided by unitless, so unit is again megapascals. The reason, again, just to iterate, I'm talking about megapascal is because majority of the measurements which we take in terms of specimen geometry are in millimeters, they are not in meters. Pascal is defined as newtons per meter square. So just because our measurements are in millimeter, we cannot typically see things in pascals, because it will be a very high number, then we'll have to use a lot of decimals. So better scaling is megapascals, right? It's not like things come only in megapascal, but it's a better scaling method to just make sure you can see something in the plot. Otherwise the plot will be extremely low, right? Another thing to consider, you want to select a load cell or load cell sensitivity, which is measuring your force within a certain range. So if I use a UTM which is used for testing civil engineering structures or huge pillars or concretes for testing a soft tissue, will it work? The answer is no, right? It has a different level of sensitivity. So even if 300-400 newtons up and down it goes, it is not going to like measure it very nicely, like for a big structural UTM, like it will probably see that as an error. But here all your specimens are tested within, let's say, 100 Newton limit. So based on what are the ranges of forces in which your specimen can lie within, you have to select that what is the right load cell for force measurement. So if my maximum force which is possible for skin or majority of the soft tissue is, let's say, 100 newtons, then I would take a 100 Newton load cell, right? Which can give me a reasonable set of values. But if you feel like it could go to 200 newtons, you may take a 0.5 kilonewton or a 500 Newton load cell, right? That will give you the right sensitivity. If I use a 1 kilonewton load cell, it will not be able to measure the small subtle differences like 1 or 2 newtons. It will not be able to measure. That will be an error. If I take a highly sensitive load cell, let's say 50 Newton load cell for a 100 Newton max, then it will be extremely sensitive, right? So both are not very good ideas. The idea is be in the right ballpark estimate and select the right load cell. So having said that, what my lab uses in IIT Delhi, we have 3 or 4 different load cells. We have a 1 kilonewton load cell which is 1000 Newton. We have 100 Newton load cell. We have 1 Newton load cell also for very soft tissues like the brain, right? So all these load cells, we replace them. They are easily replaceable with the machines depending on the kind of application or the tissue which we are testing, right? So another thing to note here is, while we are talking about the modulus of elasticity, what I had just indicated, this is not like the hard materials or the metals. The slope keeps on changing. So can you define a single modulus of elasticity for this entire simulated model, like which is the stress versus strain or the model response? You cannot. So there is a range of modulus of elasticity which you want to describe or report. Let's say the modulus of elasticity goes from 20 megapascal to 75 megapascal. This is how you have to define. And there are much more advanced models which are known as hyperelastic curve fit models or nonlinear curve fit models, which I will be describing as a part of this course, which will give a much more accurate fit. You do not need to define a modulus of elasticity, because typically modulus of elasticity is not constant. So it's not a good value to assume that if I take a 100 megapascal modulus of elasticity for skin, that's not a correct assumption. So if any of you are working in research or any other field and taking a modulus of elasticity value and using it for any soft tissue, that is highly inaccurate. That is a myth to be busted, right? So let's go further. The next type of test which is very common is known as a biaxial test. So what happens in a biaxial test, as the term suggests, it is not along a single axis, but it is along two axes, two different axes which are perpendicular to each other. So a planar tissue specimen rather than a rectangular kind of tissue specimen, planar, which is usually in the form of a square, not unbalanced typically, is clamped orthogonally in a way that load will be applied in the both directions, right? Along both directions, one side clamp will be fixed. The clamps which are not fixed will be displaced at a certain rate, right? So what you're seeing here in the figure here is this particular soft tissue, most likely from the brain. It is very difficult to clamp with the system. So there are certain hooks which have been placed which are further attached to the clamp, right? So here you have 4 different arms or 4 different clamp attachments. one clamp in each direction is going to move and one clamp in each direction is going to be fixed. Same will happen in the other direction, right? So this is how a biaxial test is conducted. Having said that, I'm going to introduce you to all the instruments as we go along. This is a typical introduction to the biomechanical properties of the different soft tissues, but we will be then talking about in-depth measurements and how every device looks like and what are the key steps and whatnot, right? So yeah, so you typically apply a strain rate very similar to the uniaxial test. You displace the specimen at a certain rate or a displacement rate in each direction. If you place the same strain rate in both the direction, it is known as a equibiaxial loading. If it is not the same strain rate, one is being pulled at a much more higher rate, then it's a non-equibiaxial loading. Why would you need a non-equibiaxial loading, or why equibiaxial loading? These are dependent on the different applications, right? So for example, let's say a brain impact is exposed at a certain location which is causing equal loadings, right? So that can be taken as a equibiaxial loading. But let's say you talk about skin has fibers in one direction, so it doesn't undergo equibiaxial loading in majority of the times. There is loading which is natural tension of the skin is different in both sides, so that will undergo a non-equibiaxial loading, right? So those kind of aspects come in, but after a certain point, very similar protocol, and beyond certain strains, the tissue tends to rupture. When you keep on pulling it in two different directions, it's going to rupture even more quickly, right? Because there is not only independent pulling along the two directions, there is also an interplay between the two directional loads and its effects. So when I pull something here along this direction, it is going to affect that direction as well through the effect which we known as Poisson's effect. Poisson's ratio I would like to introduce in a much more better fashion, but I will just quickly describe what it is. It is a measurement of how much contraction or how much change in the specimen would you observe when you apply a load vertical to that direction. So when you apply a load to a specimen uniaxially, you will see some contraction. That is because of the Poisson's effect. What is it like from an engineering measurement standpoint? I am going to explain in the upcoming classes, right? So due to this Poisson's effect, there is an interplay between the two directions, and finally you see that effect as well, like in the stress strain plots, right? So there are two load cells in two different directions, and both load cells are independently uh, collecting all the information and timestamp based data on the forces which are being applied, and the displacements are also measured. So independently you find out the displacement along this direction, displacement versus force, and also the force versus displacement along this direction, right? And the interplay is already taken into account. You're not worried about that, what is going on. So you just take the measurements in both the sides, right? So during the experiments, very similar to what happened in the uniaxial tests, the fibers within the tissue stiffens and it aligns more towards the load directions. So if the fiber is somewhere in between, it will try to align towards one of the load directions, or if there are multiple layers of fibers like I described for several soft tissues, they are going to find their own direction which is the best path and kind of organize themselves along that direction, and that will cause the overall soft tissue response to stiffen or go up, right? Again, the pull force, displacement, stress and strain definitions are the same, right? So now the only change in that definition is they are being looked at in each direction. So along, let's say this is the x and y, you can see this designation here on the figure on the top. So if I consider this side as the x and this is the y, so I find out the pull force versus displacement points along the y direction as well as along the x direction, and I separately find out the stress and strain for x and y, right? That's the only difference. Whatever I did for the uniaxial test, I am going to repeat that for both the directions. Next, experimental data is generated along the two axes by a biaxial testing machine. So biaxial testing machine is usually there. They are typically very expensive machines. So we have also developed a few machines in our lab. because they would all cost like 40 to 50 lakhs or so forth, like in the Indian system. So it's better to develop one, it's much more easier to use, right? So we have developed a machine like which costs us less than 50 or 60,000 rupees, like, so that was really valuable in doing the biaxial tests. And after that you find out the modulus of elasticity, which is again along the two different directions. So you will have a separate x direction modulus and separate y direction modulus, right? So with this, what do you end up with? You end up with a plot as it is shown on the right bottom, which is given as a stress versus the bottom one is given as a stretch ratio. Stretch ratio is nothing but just the number 1 added to strain. The strain will typically start from 0 and kind of go up. Stretch ratio, why do we introduce this term? Because this is often used interchangeably for a lot of different mathematics which goes along with the understanding of the mechanical responses of the soft tissue. So I'm going to explain about stretch ratio later in the classes, right? But let us just assume it's strain plus 1. The entire plot is being shifted by the number 1, right? Yeah, so stretch again is unitless, similar to strain. You're looking at the stress on the y-axis. Here you're looking at two plots. One thing to notice on this plots are these are just not only hard lines like the orange and the blue one. You also see some eye-shaped, features here. Those are known as the error bars. So in any kind of experiment, any kind of mechanical experiment, be it with soft tissue or be it with any other material, you need to repeat an experiment at least thrice or even more, right? At least thrice. If you repeat the same experiment at least thrice, then you will get a range of values which will not be entirely the same. So based on that, based on using basic statistics, you define the standard deviation. That is what is being described by the error bars. So what is the deviation in the results which can happen if I have cut 3 specimens of skin from the same location, same direction, and I have tested all of those 3? Where they perfectly aligned curves, that can never happen, right? There is always some imperfections and little bit of interplay, because tissues are very, very complex and nonlinear. Once you change the location or things a little bit, it is going to change in response. Similar with materials also, other materials. Error bars are very common. So without an error bar, you can never report any of the experimental results. This is very important to note for all of us, right? Every experiment should at least have an error bar. So again, we are looking at the stress versus strain profile, where we are seeing two different profiles, not very different, and with having their own error bars. One is along the x direction, one is along the y direction. The difference would be due to the interplay which I have said between the x and y direction as we pull them in two different directions, right? So that's the only difference which I can notice here. Let's go further. Okay, so we have talked briefly about the two top tests which are commonly conducted. One is the uniaxial tensile test and second is the biaxial tensile test. These are very, very popular, and most of the other tests like multi-axial, cyclic test, fatigue test, shear test, these things are not that much common. Like, so majority of the research papers or research works or any industry tests are usually around that uniaxial and biaxial only. More uniaxial than biaxial, actually, much more uniaxial, right? So having said that, what we have done as a part of our research, we have started to collate all the different biomechanical properties of the tissues. Why did we do this? Because we found a gap that whenever you start looking at the different soft tissues which exist along the different parts of the body, let's say the brain tissue or the skin or the foot tissue or something else, like all the different described organs which I've mentioned in the previous session, all these tissues, many of the researchers have tested them and they have reported different properties. Why are the properties not very same? Because they have either used different machines. Somebody has tested it in 1990, somebody has tested it in 2003, 2014. The accuracy of the machines have changed, the type of machine, the way they have clamped the specimen, the way they have cut the specimen, the direction of the fibers. So there are so many factors which have changed, and that is why their results are not very much comparable. That is not a good thing, like if I as a new researcher, or you as a new person who is trying to devise a medical equipment, is trying to look at the properties of skin, you should get a single property. You should know like what is going on, or a range of clear properties. You should not be digging at 5 different papers or 5 different areas and finding different values of those properties. So this is a gap which we realized in the area of soft tissue. Everybody, if you are a biologist, you are a biomedical engineer, you are a biotechnologist, you are a medical device engineer, you work in any area in the healthcare, or you are a doctor who is trying to understand the mechanical properties of soft tissues, you would have been looking at it at a very isolated way. If you are interested in brain tissue, you would look at brain tissue. If you're interested in skin tissue or an arterial tissue, you look at that. But finding the definitive literature which reports that correct or the actual values are limited. You have a lot of literature, but you cannot compare and correlate. So what we did was we collated all these values which have been reported so far up till 2021, and this is the table what you're looking at in the bottom. So I'm going to quickly go over this table and just take you through some of the properties, right? So let's take a look. So the first one is skin tissue. Here the skin tissue, you are seeing two subgroups. One is parallel to the Langer lines and one is perpendicular to the Langer lines, right? I have already mentioned what Langer lines are. They are typically the fiber lines. You are seeing some elastic modulus which are fairly different. You are looking at one group which is not clearly highlighted what their directions of the specimen was. That is the first one with a blank, right? That is reference 49. These are some set of references which we have looked at. I'll indicate you to the key review paper or the key book from which we have taken that, and you can look at that. So parallel to the Langer line, you're looking at a 160.8 plus minus 53.2. That's the error bar, right? That's the standard deviation, megapascal. That means the skin tissue modulus of elasticity can vary from 160.8 plus 53.2 up to 160.8 minus 53.2, right? The ultimate tensile strength, this is another important aspect. Modulus of elasticity, we have quite well understood that this is the slope of the stress strain profile. Ultimate tensile strength is the maximum strength a material can endure before it undergoes rupture or a break, right? This is typically defined for hard materials, but for soft tissues also very similar. The ultimate tensile strength of the soft tissues, you cannot stretch it beyond that limit, it's going to break. That also you can see very clearly along the Langer lines, 28 plus minus 5.7 megapascals, perpendicular to the Langer lines 15.6 plus minus 5.2 megapascals, right? Shear modulus, how this skin tissue behaves in shear is not very well defined. So what I'm trying to indicate here is shear modulus, if it is not well defined, and if you're a researcher interested in understanding skin further, this is an area you may work on, right? So that's what the indication are. We are trying to figure out what is the latest information we have and the state of the art information we have that we have collated. Wherever you see these blanks, those are the gap areas in which no information or not a legitimate kind of information is available, right? Next is muscle tissue. You have several different muscles which have been characterized in literature, like the biceps, the flexure muscles, the soleus, the gastrocnemius, skeletal muscles, temporal muscles. Majority of them do not have any property which is described or which has been tested by any researcher around the globe which talks about the elastic modulus or ultimate tensile strength. But a lot of these researchers have worked on the shear modulus. How do you find out a shear modulus? I'm going to explain in the upcoming sessions. Shear is nothing but when you pull something sideways, right? So that shear modulus sometimes becomes really important about peeling of skin, or like cutting through the skin and things like that. The next is the tendons. Before that, temporal muscle, it has been pretty well defined in terms of elastic modulus, ultimate tensile strength, but doesn't have any reported shear modulus, right? Connective tissues, you have the Achilles tendon, then tendons in general, and then the ligaments Patellar ligament and the ankle, these are pretty well defined and the numbers are right here, right? Elastic modulus is very well defined, but the ultimate tensile strength when they can fatigue or fracture, fatigue is a little different, when they can actually fracture is not very well defined. So this is an area still which needs to be explored, right? And shear modulus again not well defined. These are some of the citations for the same. Next is brain tissue. Brain tissue, white matter and gray matter. uh, Several of the researchers have reported, like 114 citation, 115, these are indicative. I'll explain what that is like in the, you can find them in the book, reference book, or the review article which I'll share, right? So these are some numbers, very low numbers, you are looking at kilopascals, 3.66 plus minus 0.12 kilopascals, right? And 2.80 plus minus 0.14 kilopascals. So the white matter and gray matter properties are a little different, right? Similar, not very similar, but another one, proper set of properties have been reported by some another research group. You can see the difference in the properties. The first one is 3.66 plus minus 0.12. The second one is 1.89 plus minus 0.59. Quite a bit of difference, right? So this is because of the difference in the specimen collection, the machine, and so many other factors. Next is nasal cavity. These are all the different tissues which we have discussed in the first few sessions, their structures and how they look like. Nasal cavity, it has been defined, the modulus of elasticity. The septal cartilage, aral cartilage, and the septal cartilage, again like by another group, have been defined with properties such as follows, right? And then the ultimate tensile strength of the nasal peristonum is also defined, but the shear modulus is not known. The from the oral cavity which we have studied, the gingiva, hard palate, buccal mucosa, uvula, soft palate, all these properties are fairly well defined, right? By just a few researchers, not many researchers are working on these areas. So finding a lot of values does not necessarily mean a lot of people are researching in it. Still the top research areas are still the human heart, liver, or the skin and the brain. These are the top areas. These areas, if you look at the citations, almost the same papers like have reported certain values, right? Like, so there may be 4 or 5 significant researchers, right? Then the tongue, also 6 kilopascal, fairly soft. 3 different research groups, or almost 6 different research groups I can say here, have reported the values. Tonsils, one group has reported some value, but ultimate tensile strength value of any of these soft tissues are unknown. So what that means is, if you want to test a tonsil tissue, you can test it until it ruptures and report that value. That research would be a valid research, right? Going further, you're looking at esophagus, very little information, just ultimate tensile stress value is known, and one research group has talked about 4 to 14 kilopascals, which is the basic modulus of elasticity. Lung tissue, lot of the research groups have described the properties again in kilopascal. The human heart tissue, the specifically the pulmonary valve and the aortic valve, these properties has been described, as well as the ultimate tensile stress properties have been described. The breast tissue is also another tissue which is widely studied at different levels of pre-compressions, like 5%, 20%, and glandular tissue, adipose tissue, normal fat, fibrous tissue, all these properties have been well defined, but not the ultimate tensile strength. Liver tissue has been very well described. These are some of the properties you can use directly for your research or any other work. Under compressive and loading and tensile loading, they have different properties. Also for males and females, they have been described by different works, right, in the research. Also, you're looking at some ultimate tensile stress values. Gallbladder has been clearly defined along the axial loading and transversal loading directions, like these are 2 different directions based on the fiber orientation. You're looking at both the elastic modulus properties as well as the ultimate tensile stress properties. Stomach tissues, spleen, pancreas, colon, small intestine tissues, majority of them have been described, but not with a lot of literature research groups. So these are some of the properties we have collected for all of the researchers out around in the globe in form of a review paper, and we have stated them in a book, and they can be used directly, and they are the latest properties. Now you do not need to dig for 10 other different papers or publications which has reported any property, right? This can work as standalone. Kidney tissue properties have also been reported, so as for the urinary bladder. Uterus tissue is very interesting. They have reported a lot of different properties for the anterior cervical lip, the cervix, anterior cervical lip, posterior cervical lip, and the cardinal ligament, round ligament, uterosacral ligament. Very, very important aspects of the or components of the uterus tissue or the uterus organ as a organ, and all these properties have been very well defined, majorly for understanding the female pelvic system. The last one is vaginal tissue. This is also being defined for the postmenopausal and the premenopausal with different properties, right? Okay, this is something to consider. So how do the properties compare? So let us talk about the three plots. So the very plot on the very left talks about the extremely soft tissues. So you are looking at modulus of elasticity going from 0 to 0.08 only. Out of these, the softest tissue is the human brain, right? Followed by lungs, tonsils, stomach, tongue, esophagus, and the hardest out of these extremely soft tissues are the breast, with a lot of variation. The next plot is in between, where we are looking at 0 to 0.8, not 0.08 as we saw in earlier. So these are medium grade softness tissues. Out of this, you are looking at liver, gallbladder, uterus, and kidney. One thing to note here is wherever you see a huge error bar or the I kind of symbol, that means the properties vary a lot from one person to another. Like uterus properties do not vary a lot. That's what it means. Liver properties vary a lot. The last one is soft tissues, which are much more harder. They can go from the skin, which is the strongest. So skin is the strongest soft tissue in the human body, followed by the oral cavity, the heart, the vaginal canal, small intestine, and then almost negligible muscle, nasal cavity, colon, and urinary bladder. So very interestingly, you would always imagine muscles are much more stronger than the skin, but that is not the case here. So this is a plot to be considered well in detail, and you can very clearly see the softest, medium softness, and the hardest soft tissues which are located all across the human body. All this information you can find in this first book, Mechanical Properties of Human Tissues, and this is already available with Springer, and this is all these detailed properties. Also there is a review paper which is based on which this book was originally written, that will also have the properties. Another book, Materials for Biomedical Simulation, also has adaptations of such properties, right? So with that, I would like to thank you, and we will keep on continuing digging in more into the mechanical properties of soft tissue and learning some very exciting lessons into how to do the characterization and look at different applications. Thank you all.